Welcome to Breaking Math, the podcast where we can freely question why machines learn. And we get to learn more about the mathematics behind your favorite AI tools like ChatGPT, Sora, and Gemini. Today, we are joined by Anil Ananthaswamy. He's an award-winning science writer and former staff writer and deputy newsletter for the London-based New Scientist magazine. He is the 2019-2020 MIT Knight Science Journalist Fellow. He writes for Quanta, Scientific American, Nature, New Scientist, and many other publications. His first book, The Edge of Physics, was voted Book of the Year in 2010 by UK's Physics World, and his second book, The Man Who Wasn't There, was longlisted for the 2016 Penn E. O. Wilson Literary Science Writing Award. His third book, Through Two Doors at Once, was named one of Forbes' 2018 best books about astronomy, physics, and mathematics. His new book, Why Machines Learn: The Elegant Math Behind Modern AI, was just published today. Anil trained as an electronics and computer engineer at ITT Madras for his bachelor's degree, and the University of Washington, Seattle for a master's in science and electrical engineering, and later worked as a distributed systems software engineer and architect before switching to writing. He studied science journalism at UC Santa Cruz. Now, with Anil's impressive background, let's dive into this rich history of mathematics that drives machine learning. Hi, Anil. How are you doing today?
Hi, Autumn. I'm doing well, thank you.
Thank you for thank you for coming on. Now, out of curiosity, where did you start with the book originally? What was the inspiration for it? I know that Why Machines Learn has a fair bit of math in there. Tell us about why you wanted to write a book that had a lot of math in it.
So I've been a journalist for about 20 years. I used to be a software engineer before I became a journalist.
Mm-hmm.
And for a long time, I was writing on topics like astrophysics, cosmology, neuroscience, particle physics.
All the cool stuff.
All the cool stuff, yes. But what was interesting is that when I would write about those topics, I would try and understand the science as best as I could and then not write about it. I never had any illusions about being able to actually do that work. But over the last sort of around 2016, 2017, I noticed that I was writing more and more stories about machine learning. It was just beginning to ramp up. I think every time I would interview the sources and start talking to them about what they were doing, I think the software engineer part of me woke up. It had been dormant for 15, 20 years. And so some part of me really wanted to learn how to sort of code and build these systems. And in 2019, I got a fellowship at MIT, the Knight Science Journalism Fellowship. And as part of that fellowship, I did a project learning how to code. And going back to class, I literally went back to CS1, sat with all these teenagers learning Python coding. It was intense. As I started coding, I realized that I really wanted to learn the basics of machine learning, not just core, blindly. So I started listening to a lot of YouTube lectures by professors. And one particular professor at Cornell was very instrumental for enjoying the subject. And it was when I was doing that, I realized that mathematics underlying machine learning is beautiful. And now the writer in me woke up and said, "Oh, I have to communicate this to read it."
Precisely.
So that's how it came about. I find it was a book that I would have liked to read myself when I was trying to learn machine learning. Some combination of storytelling, journalistic storytelling, history, sociology, and the math. So but it's really the kind of, I found the math really lovely. Now I wanted to get that across. So hence the book full of equations.
I think that that's crucial for anybody who either needs a refresher or, you're switching fields, anything of that sorts. And sometimes even when you're really advanced in the field, we need to take a couple steps back and think about the story behind it. and have that appreciation for it. Because I know I'm an industrial engineer by training, and I deal with a lot of robotics. But sometimes when I was teaching a course before, you kind of have to pick and choose. What do you want to teach somebody for the simplicity? And I think that this book it's crucial for people to have, even if it's needing that refresher for stuff. It really highlights everything that you need to know.
Is your vehicle stopping like it should? Does it squeal or grind when you brake? Don't miss out on summer brake deals at O'Reilly Auto Parts.
O'Reilly Auto Parts.
Save on O'Reilly Brake Parts Cleaner. Get 2 cans of O'Reilly Brake Parts Cleaner for just $8. Valid in-store only at O'Reilly Auto Parts.
O'Reilly Auto Parts.
Of course, this is my subjective take based on a lot of research and a lot of conversations with the experts. A lot of work I found was the beautiful and essential part of machine learning. I'm sure someone else might have a slightly different take on what is crucial. You can only put so much into a book. It's already almost 450 pages long. And so I have to do some crucial algorithms probably. But I think my intent was to get in the conceptual arc of machine learning, not just the algorithms strictly, that contain the ideas that underpin ML. I will not just focus on deep neural networks because those are this is the phenomena that has been so much other one that has happened. So yeah, I agree with you that then the book like I said, either as a refresher for someone who has a background in it, but also people who have maybe high school level or mathematics and they want to understand ML at a depth that is more than what you might get from reading magazines, popular science.
And absolutely. It's beyond that. Now, besides appreciating the beauty and elegance of some of the basic math behind machine learnings, what are really the other reasons for writing the book?
I really think that watching how AI is developing and watching the big companies that are kind of becoming the gatekeepers for this technology, I feel like we need a layer of society that, apart from the people building these systems, we need a layer of society that really understands what's happening at least a certain amount, at least a certain amount of mathematical related. Because it's only when you look at the math behind machine learning that you start understanding both the power that is inherent in these systems and also its limitations.
Correct.
So we need, we need communicators, science communicators, journalists, policymakers, teachers, and just about anyone in society who's willing to be engaged with this technology at the level of at least the basic math. Yeah. So we need society to be on gatekeepers also, not just even from the people who are building these systems. And I think for me, that's really important, to convey the mathematical basis for this.
I agree, because so much decision making is made now through AI. Whether it's social media, you can run a quick code on ChatGPT or Gemini or whatever you have available to you, right? Or someone builds an in-house algorithm for a company. You need to know what decisions are being made, and sometimes there's those very subtle, those algorithms may have implicit bias. You don't realize that until you code it a few times.
Yeah, absolutely. And I think when you understand the mathematical basis for why these algorithms work, the reasons for the bias also become obvious. So you can understand where the bias comes from, whether it's from the data or whether it's from the choices you make of the algorithm, etc. And the math conveys that in ways that just language is unable to. I mean, we can talk about it in plain language, but somehow the math just needs its own pace.
Yes. Now, We talk about what's obvious, and most people already know that AI is sometimes ChatGPT, but it does have a history as well. Tell us a little bit more about that, because people don't see the history and evolution of this.
Yeah, I mean the history of machine learning goes back a long way. I think for most people now, artificial intelligence or AI is literally just ChatGPT. Yeah, and your
Right.
ChatGPT is being used as a kind of placeholder for all kinds of large language models. These aren't the new one or the. But the history goes back, at least a certain kind of history, like for instance, the history of neural networks. They go back to the late 1950s. So Frank Rosenblatt was the first one to come up with an algorithm called the perceptron algorithm, which is essentially a single-layer neural network that could be trained to, do classification. For instance, if we try to distinguish between patterns of two kinds of images, and the idea was that these images somehow occupy some coordinate space where one type of images were in one type of one location in the coordinate space, and the other images were in another portion of the coordinate space. And you could draw a straight line between the two kind of classes of images. Then this algorithm was guaranteed to find that linear divide in finite time. And this was a really big deal in the late 1950s, early 1960s. Um, and also there was Bernard Vidro, so Vidro with his swirling Chekhov came up with the least squares algorithm, also for training a single neuron, a single layer neural network. And at that time, in the late 1950s, early 1960s, that's all they could only train a single layer neural network. And the neural network essentially was composed of artificial neurons. Artificial neurons are very, very loosely inspired by biological neurons. I think should be very clear that the term artificial neural network somehow seems to suggest that these things are as complex as biological networks. They're not. So the
Exactly.
artificial neuron is just a computational unit. It takes in some inputs, does some computation on them, and then it is explained to produce an output or what kind of output to produce. Right? And the artificial neural network is said to be the network of these artificial neurons. And if you actually look at a biological neuron and what's happening in a biological neural network, the complexity of that is so, so much greater. Right? So
Yeah.
nonetheless, these are artificial neural networks, and it's still it goes back to the late 1950s, early 1960s. But what happened at that time was that these were singular neural networks. People didn't know how to train any more complicated neural networks. Like if you try more than a single layer, we didn't know how to train them. And around that time, two other AI researchers, Marwan Yuski and Simon Pepper, came up with it's a very, very beautiful authoritative book called, it's called The Resurgence, in honor of Frank Rosenblatt. But in that book, they kind of showed that the single layer neural networks could not even solve a simple problem. It was called the XOR problem, where if the data that you had was of a kind where you couldn't draw a straight line through the coordinate space to separate two classes of data, and this neural network, just single neural network, just couldn't find the solution. They had mathematical proofs for that. But they also kind of suggested that even if they suggested it without proving it. They suggested that even if you had multiple layers in the neural network, you still probably wouldn't be able to solve that. And that kind of put a huge damper on neural network research. People just kind of stopped thinking about it and wondering, because they thought, oh, this is not linear. So pretty much, towards the end of the 1960s and early 1970s, the research in neural networks just fell off a cliff. But meanwhile, other algorithms were beginning to
Yes.
develop, and a lot of machine learning history has to do with non-neural network based machine learning algorithms.
Now, tell us a little bit more. While research on artificial neural networks did come to that big standstill, what were the other breakthroughs that were happening?
Oh, I think again, this is subjective. This is my take on what was happening. But I thought the K nearest neighbor algorithms was a conceptually brilliant piece of work that also came out in the 1960s by Franz Faber and Peter Hart from Stanford.
Yeah.
right? The cover art to have 10 years in Alvin. And that was, conceptually so simple. Like you basically, think of your images as, each image is converted into a vector, and the vectors are plotted in some high-dimensional space. So let's say, images of cats in one side of the coordinate space and images of dogs on the other side of coordinate space. Then you get a new image. You convert that into a vector and you kind of plot that in the same coordinate space and see what is it nearest to. Is it nearest to dogs or is it nearest to cats? And, depending on that, we classify the image as a cat or a dog. And of course, it sounds very simple when you say it like that, but the underlying math that tries to make a formal case for it was extremely complicated. But they managed to show that it's an algorithm that does really, really well. I mean, that was a big breakthrough, and it was very powerful and was used for a long time. It runs into this problem called cursor dimensionality. As you start getting into higher and higher dimensions, data starts behaving in a very strange way. And so as the dimensionality of the data were very big, the k-nearest neighbor algorithm started, again, not doing so well. So in terms of, computational efficiency. And then I think, and there was a lot of work to do with, the naive Bayes classifiers or polar Bayes classifiers. So that's also significant chapter in a book where I'm getting the reader to appreciate the probabilistic aspects of machine learning. We seem to think that when machines make a prediction, that they're certain about what the prediction is, but actually under the hood, a lot of these things have uncertainties. So there is a certain amount of uncertainty in a prediction that can be quantified, or the algorithms are explicitly probabilistic, and they're essentially choosing the most likely answer. It's very possible that the slightly less likely answer is the correct one, but it chooses the most likely answer. So, so understanding these kinds of uncertainties and probabilistic aspects of machine learning algorithms also, from the mathematical perspective, makes a big difference in appreciating what's going on. Probably for me, the most influential and important algorithm prior to neural networks were support vector machines. So I was saying about Rosenberg's perceptual, which finds a linear divide between two classes of the data. Now, if you imagine two clusters of data in coordinate space, one on the right side and one on the left side, and there's a little bit of gap between them. In principle, you can draw an infinity of straight lines through that, through that gap. It can be a straight line or a plane or a hyperplane or whatever, depending on the dimensionality of that data. But in principle, you can have an infinity of them, and the perceptron does not find the most optimal one. It just finds any, divide between the two clusters of data. Support vector machines were the first ones to find what's called an optimal margin classifier. It basically finds the linear divide between the clusters of data that is as good as possible, not any old separation between the two. And then the other thing I was telling you about the dimensionality problem, one of the wonderful things that support vector machines also do is they use these things called kernel methods. And kernel methods are just this really, really amazing sort of mathematical trick where you take linear data where you cannot find a linear divide, because the data is so mixed up that you have to draw some really convoluted curve to separate two clusters of data or three clusters of data, whatever. And so the idea would be to project this data into really, really high dimensions, possibly even infinite dimensions. And that even, it boggles your mind to think what infinite dimensions could be. But in order for support vector machines to work, they have to do dot products of vectors representing the data points and your new data that you're dealing with. Now, if you're going into very, very high dimensions or even infinite dimensions, storing these vectors or doing the dot products is computationally really expensive. So what kernel methods do is they find a function that allows you to take two vectors, and that function produces a dot product not of the vectors in the lower dimensions, but the dot product of the vectors in the higher dimension. So you can get the dot. You basically, let's say there's a function k of two vectors x and y. then
Okay.
the function k gives you the dot product of x and y not in the lower dimensions, but as if these vectors were projected into the higher dimensions. So you basically are able to do computations in the higher dimensional space without actually ever converting your vectors and stepping into the higher dimensional space. So you computationally you're doing your work in the lower dimensional space, but the effective results you're getting represents work happening in the higher dimensional space. So in the higher dimensional space, you can find a linear divider. And it turns out these
Gotcha.
linear classifiers are beautiful. So you work in the high dimensional space, get the linear divide, and then you project back into the lower dimensions. And in the lower dimensions, that straight line looks like a very convoluted curve. So you essentially ended up finding a nonlinear boundary between two classes of beta. Because you projected your beta up into high dimensional space from this, linear classifier, and then projected it back. But computationally, you're always working in the lower dimensional space. And that, I think, is just amazing.
That it actually is. Because you wouldn't think of that if you're, I don't know, like taking the probability of something and just writing it out mathematically, so simplistically. But how do I put it? It's the skip the middle fluff of the problem, and you just get that output. So it saves a lot of computational time.
And it's quite craft and art
Yes.
to design these kernels. There are lots and lots of different kinds of kernels, and they become more and more mathematically sophisticated. So that's a separate field in itself.
Yes.
So you could design these kernels, like what you do, what kinds of things do you project into the higher dimensional space? What are the features in higher dimensional space that we're working with? But that's there are textbooks written on that entire thing by itself. So
Exactly. What's really so special about support vector machines and kernel methods?
I think the specialty is really that support vector machines find what are called optimal margins. Like if you have two classes of data and you want to find a divide between those two, like you want to find a straight line or a curve that separates those two classes of data. So that when you get a new class of data and you want to figure out does it belong to class A or class B, you want to be able to do that as correctly as possible. You'll always make some mistakes, but if the dividing line that you found between the two classes of data is optimal, then the mistakes will make when you're classifying unseen data is lower. I mean, there'll always be mistakes, but you're basically lowering your probability of making mistakes. So that's support vector machines. But support vector machines find a linear divide between the classes of data, and they'll work in any dimensional space. But if you keep going into higher and higher dimensions, then it gets computationally intractable. So that's where kernel methods come in. The combination of support vector machines and kernel methods. What kernel methods do, like I just said, is they will project the data into high dimensions, find the linear divided high dimensions. The computation is all happening in the lower dimensional space. So usually you're finding some straight line in, 10,000 dimensions, 100,000 dimensions. It doesn't matter what it is. It could be even infinite dimensions. In infinite dimensions, you will always find a straight line to separate two classes of data. But when you project that back into whatever dimensions you started with, 100 dimensions or 200 dimensions, that straight line turns into a very nonlinear curve. And so the combination of support vector machines and this ability to find a straight line in higher dimensions without computing in higher dimensions, that's the power of support vector machines. And they have been used for all sorts of classification problems prior to neural networks becoming a big deal.
Okay. Awesome. Now, as we see machine learning progressing on multiple fronts, where do artificial neural networks start coming back into the fray? When did this happen and why?
So I mentioned earlier that when HK Pepper kind of made this case against single neural networks, saying that they couldn't even solve the XR problem. A lot of people dropped research on that, in that field. But there were a few, there were people who persisted. Again, in my book, I take a few examples of the kinds of work that kept going on. So one big development happened in early 1980s. John Hopfield developed something called Hopfield networks. Hopfield networks are essentially, again, a certain kind of architecture of these artificial neurons. They are connected bidirectionally. So, normally in a neural network, you have the input coming in from one side, goes into one layer of neurons. That layer of neurons produces an output, and that goes into a subsequent layer.
At Baker's Pharmacy, care is what's most convenient for you. Care is being here when you need us. We're open evenings and weekends. Care is helping you save more. Most insurance plans and discount cards are accepted at your local Baker's Pharmacy. Care is saving you time by managing your prescriptions online. You can request refills, check order status, and more. Care is convenience that works for everyone. Baker's, a world of care is in store. Services and availability vary by location. Age and other restrictions may apply. For coverage, consult your health insurance company. Visit the pharmacy or our site for details.
Save on O'Reilly Brake Parts Cleaner. Get 2 cans of O'Reilly Brake Parts Cleaner for just $8. Valid in-store only at O'Reilly Auto Parts.
O'Reilly Auto Parts.
And it keeps going in one direction. These are called feed-forward networks. So the output of the neuron never feeds back to itself or to neurons in the layer before it. So those are the standard things that we see today, these feed-forward networks. John Hopfield developed a slightly different architecture, where you could have recurrent connections where a neuron's output could feed back into other neurons in its own layer. So you did this, bidirectional neural network, and he showed how you could store memories in these networks. So what you do is you essentially figure out how to store an image in such a network, and the basic idea there is that if you can adjust the weights of the network such that when you store your image, the network has what is called a minimal energy. Then there's a way of defining what the energy of a neural network means in this context. But the math shows you that if the image, if the outputs of the neuron represent pixels of an image, let's say there are 100 neurons, right? And each one of those neurons is outputting something, and you take that as the value of a pixel, so you've got 100 pixels, and that's a 10 by 10 image, right?
Yes.
So if you store the image in this particular Hopfield network, then the math shows that that network is basically at its lowest energy state. And now what you do is you perturb the network, right? You change some of the pixel value. So starting if the image is corrupted, and you've got all sorts of noise in it. But the dynamics of the network is such that it wants to go back to its lowest energy state. And so if you perturb the network, which means you have perturbed the memory of the image, then the dynamics of the networks are such that it will just basically all the neurons will start firing in response to the nearby neurons, and eventually they will all settle back to this state that represents the minimal energy state. And now when you read off the output of the neurons, you're going to get back the original image, because that image represents the low energy state, or the lowest energy state. So that was a very big deal in 1982. And John Hopfield came up with that. It's not depending on networks that we used to hear, but it was like the beginnings of the return on neural networks. Probably, again, there are other things that happened, but I think the real key development was 1986 when Blumenbach, Hinton, and the others came up with the backpropagation algorithm. This was finally, I have to make sure that we get the history right, in the sense that this algorithm is often attributed to Blumenbach and Hinton and Jens, but the idea of backpropagation goes all the way back to Frank Rosenblatt in the 1950s, the late 1950s, early 1960s. He knew that in order to train multi-layer neural networks, which have more than one layer, you need some kind of algorithm. He actually called it backpropagation in his book, but did not know how to do it. And from the 1960s all the way to the mid-1980s, there were various people who attempted to solve this problem in different ways, not necessarily for neural networks. There was stuff that was going on in control systems, in rocketry, in economics, so these ideas were all there in different forms, but it was the Rumelhart, Hinton, Weir's paper that clearly showed how to do this for weak neural networks. right? Deep here simply means that the neural network has one layer that is sandwiched between the input and output layer. So it's hidden. It's hidden from the input side and it's hidden from the output side. So any neural network which has at least one hidden layer is technically a deep neural network, and that requires the backpropagation algorithm to train it. And so that was a big deal in 1986. And maybe, again, somewhat subjective, but 1989 was the so-called
Yes.
universal approximation here. Now, it's one thing to say that you can train a deep neural network to do something, but it's completely another thing to mathematically prove that there is no limit towards a neural network and right? That was what the universal approximation became every day. It basically said, so there's one way to think about what the neural networks are doing. They're essentially given some input X and desired output Y. The neural network has to find the function f, like that, y is equal to f of x, right? And that function can be anything. It depends on what kind of correlation exists between your input and outputs. And that correlation exists in the data, right? So the training data is basically some form of pairs of input and output that we're providing the neural network. You don't know how the input and output are connected, what kind of function maps the input to the output. And therefore, it's like, it's like a black holes, right? So that's kind of what the neural network has. The neural network algorithm kind of figures out what the function f is that maps, y is equal to f of x, right? Now, what the universal approximation theorem shows is that if you have a single hidden layer network, at least a single hidden layer network, then given enough artificial neurons, which means given enough computation, a neural network will it will approximate almost any function that is necessary to correctly map the input to the output. So basically, it's a network, again, given enough artificial neurons. Of course, in principle, in practice, in principle that's possible, but in practice, you never have big enough neural networks. There will always be a cross-relation of the neural function, but that's what the theorem shows very clearly, that it is a neural network is what's called a universal function approximator. It will approximate any function, no matter how complex that function. And then these things were really big developments through the 1980s, right? And I think that's setting the stage for, further research. Because finally people said, okay, these things actually can do amazing things. They still didn't have the computation power at this stage to do much with it, but the principles were falling into place.
We knew that those advances weren't enough. These advances weren't enough. Support vector machines dominated through the 1990s and early 2000s. What changed?
I think in order for neural networks to become what they've become today, a few things had to change. One was the necessary for really large data sets. So neural networks are extremely data hungry, and they need a lot of either human annotated data or, just basically a lot of data. And that didn't happen until the end of the first decade of the 2000s. So we had the ImageNet sort of data set. That was one of the first real large-scale data sets for image recognition. And then the other thing that had to change was these are all neural networks are very, they do a lot of matrix manipulations. And at some point, people figured out that the GPUs that were really being used for video games, ideal sort of processors for doing a lot of these matrix manipulations. So it was a combination of the availability of large data sets, the backpropagation algorithm to train these networks, and the use of GPUs that finally sort of brought neural networks to the fore. I think they became really powerful. And that's when the first neural network-based image recognition systems, which was AlexNet in 2011, that broke through and made such a big splash. So after that, kind of neural networks have pushed aside support vector machines. It really took all these elements like large availability of large data sets because of the internet, the use of GPUs and backpropagation, all of that coming together that made the difference.
Absolutely. Now, your book ends with a look at how deep neural networks and challenging standard ideas of how machine learning works. Now, tell us a little bit about that.
Yeah, so standard machine learning theory, one of the things it says is that if your model is over parameterized, that there are a lot of different knobs that you can tune in order to fit your data. And if there are way too many parameters, then you'll essentially end up overfitting the data. You will start you don't want to overfit your data that well because there might be noise in the data. And when you overfit, you end up fitting the noise also. And so when you start then testing your model on new data, which might have different kinds of noise, you're not going to do well on the new data that you haven't seen. So if you're trying to make predictions about unseen data, but you have overfit your model to the training data in such a way that you're picking up all the nuances that exist in the training data, then when you see new data, you're going to make lots of mistakes. And so basically traditional machine learning theory says that you have to find the right balance between underfitting and overfitting. You have to be somewhere in the middle, the Goldilocks zone.
Absolutely.
But the very intriguing part about neural networks is that they are actually extremely over parameterized. They have way too many parameters, and yet they don't seem to overfit the data. They seem to generalize well to unseen data, as long as the data is drawn from the same underlying distribution. So there's something going on that we don't fully understand, and standard machine learning theory is unable to explain why neural networks don't overfit and they generalize despite having enormous numbers of parameters. I mean, when you think of modern neural networks, we're talking of 500 billion parameters, even 1 trillion parameters. Those are massive. And of course, the data is also very massive, but nonetheless, there's something about the way these networks are functioning that still hasn't been theoretically well explained.
Sure.
And so the kind of book ends at that point where we point out that we have entered what one of the researchers I spoke to called terra incognita. Basically, this is unknown terrain as far as machine learning is concerned. We have a lot of empirical evidence about how these networks behave, but we don't necessarily have a good theoretical understanding of what's happening.
Now, I know that there's always been this larger question of, are machines conscious? Is it computational? I know that you've given talks on that sort of stuff before, and maybe I'll leave this also as a teaser for future work from you, right? So you talked a little bit in the book about an example for folks when you gave a talk on like, are machines really conscious? Will they ever get to that level?
This is a really tough and hard question, not because I don't want to answer it, but I think it really depends on what one means by consciousness and what it might be. So there are certain ways of thinking about what consciousness is. If you take those definitions, then machines are not going to be conscious, because there are people who will argue that consciousness is really a property of biological systems and the way biological systems are organized, and that consciousness has properties that cannot be explained by the physics of the material world and so on. So that's a particular way of thinking about consciousness. If that's the case, it's unlikely that machines are going to be conscious anytime in the near future. But there are other ways of thinking about consciousness where it's very likely that we'll end up with machines that are conscious in the way that biological systems are conscious. They may not be conscious of all of the stuff that we are conscious of, but machines will be conscious of what they are conscious of. So it really hinges on definitions of consciousness and what we mean by it. So if you take a purely materialistic perspective on what consciousness might be, that is just an emergent property of the way matter is organized, and in this case, the matter that comprises us, the biological system, and we are biological machines, then in principle, I mean, I'm not saying this is practical or that it will happen anytime soon, but in principle, it's entirely possible that machines will be conscious.
Interesting take on it.
Yeah, I mean, it honestly, just at this point, there is enough of a lack of evidence to nail down which theory or which idea about consciousness is correct. So all of them are in the running. And depending on how the empirical evidence, sort of falls, one of these theories hopefully will start making more and more sense. And then we will be able to better say with more certainty as to whether machines will be conscious or not.
Absolutely. Now, out of curiosity, when writing this book, what was one of your favorite things to learn or relearn?
For me personally, I think just the job. So I'm like you, I'm an engineer. I trained as an electronics and computer engineer, and as an electronics engineer, you do a fair bit of math, but in those days, you didn't quite pay attention to what the math was saying or doing. So just rediscovering how powerful some of these basic ideas are, like linear algebra,
Absolutely.
calculus, probability and statistics, that all of these things underlie machine learning. And we are building machines that are learning now. And turns out that all this math that you learned in in the final year of high school or the first year of graduate school or undergraduate, that is enough to appreciate what is happening with AI today. And that to me was the most beautiful thing, that all these basic ideas that I had learned a long, long time ago and probably never paid enough attention to how powerful these techniques were, that these techniques are now front and center in the technology that is going to influence our lives going forward.
I have to agree with you on that because it took most of graduate school and then afterwards, right, to think about the processes in which you learned your first year of last year of high school, first year of college, to actually be able to understand what was going on.
Yeah.
And sometimes those gears in your head, it takes a while for them to just click and go, oh,
Yeah.
I see what's going on in that larger system.
Yeah. I mean, who would have thought, at least I didn't, that, linear algebra would be so central to what's happening right now. This idea, we all learned about vectors and matrices, and they just seem like a whole bunch of manipulating of numbers. But that's what these machines are doing. And
Yes.
all these algorithms depend on having an understanding of at least the basics of linear algebra to figure out what the hell is happening.
Exactly. Now, what is one big thing to kind of wrap this up for time-wise? What is one big thing that you would like readers to take away from this? Or learn from the book?
From the book.
Or listening to the podcast, both.
My, desire for readers in terms of when they encounter this book or the podcast is that, like we said in the very beginning, that there needs to be a whole bunch of people who are going to start appreciating and understanding the basic mathematics that underlies the technology that we're unleashing on this world. And it's almost like a responsibility for those of us who want to get a deeper understanding that we try. It's not easy, and yet is beautiful enough that if we persist, that there's both joy in kind of appreciating what's happening, but there's also the prospect of becoming more aware of, what we're in for. I mean, this technology is not going away. It's going to get embedded deeper and deeper in our society, and we can't leave this technology to just the people building it. We need others to be able to understand it enough to question them and and hold people accountable for what they're building. And I personally don't see how we can get to that point without some appreciation of the math.
I completely agree.
Yeah.
So I thank you for coming on Breaking Math and chatting with our listeners, and I'm so happy that you could join us today.
Oh, thank you very much, Autumn. This has been my pleasure.
Is your vehicle stopping like it should? Does it squeal or grind when you brake? Don't miss out on summer brake deals at O'Reilly Auto Parts.
O'Reilly Auto Parts.
Save on O'Reilly Brake Parts Cleaner. Get 2 cans of O'Reilly Brake Parts Cleaner for just $8. Valid in-store only at O'Reilly Auto Parts.
O'Reilly Auto Parts.
At Baker's Pharmacy, care is what's most convenient for you. Care is being here when you need us. We're open evenings and weekends. Care is helping you save more. Most insurance plans and discount cards are accepted at your local Baker's Pharmacy. Care is saving you time by managing your prescriptions online. You can request refills, check order status, and more. Care is convenience that works for everyone. Baker's, a world of care is in store. Services and availability vary by location. Age and other restrictions may apply. For coverage, consult your health insurance company. Visit the pharmacy or our site for details.
Save on O'Reilly Brake Parts Cleaner. Get 2 cans of O'Reilly Brake Parts Cleaner for just $8. Valid in-store only at O'Reilly Auto Parts.
O'Reilly Auto Auto Parts.
Sure, entirely.